we're going to start looking at the derivative. And first start with the definition. And let I be an interval, which is a subset of the reals. And let f be a function on that interval into the reals. And C is a member of that interval. We say that a real number L is the derivative of f at C be sure I just don't miss anything. If for all epsilon greater than 0, the way I had it written before, it says if given any epsilon, probably it's better to say for all epsilon. They sometimes will say given any epsilon, but we have pretty much been always saying for all epsilon, there exists a delta greater than 0 such that if x in the interval satisfies x minus c less than delta, then f of x minus fc x minus c minus L is less than epsilon. So number is the derivative if for all epsilon greater than 0, there exists a delta that, once again, we're real close within delta of that C, this is going to be less than epsilon, sort of a familiar form we've seen before. And we can see how we get this from calculus. So if we kind of work backwards, so what does this mean? If you kind of work backwards, you can say, okay, this almost looks like the limit, huh? Looks like the limit, because remember, that's how we kind of defined the limit. Well, actually, we did define limit this way. If for all epsilon greater than 0, there's a delta such that if you're within C or within delta of that C, then this thing minus L will be less than epsilon. Now, before we had just a function over here. Now we have something more extensive, but it's same idea. So like for example, if we work backwards, this will be, say, the limit as, now we're just going to put like x minus c and x approaches c in here, and f of x minus fc divided by x minus c, that's the same thing as the limit. In other words, if we were to define this limit the way we did before, we would say if this limit was equal to some L, then we would say for all epsilon greater than 0, there exists a delta such that x minus c less than delta. Then we would have this, whatever is here, minus L less than epsilon. So that's really just a limit. Again, you remember, and this is what you had like from back in Calc 1 when they first introduced the derivative. So this is basically f, say, prime at a particular point. You remember it was probably right near the beginning of Calc 1, probably way back when for some of you, that you had the limit, the derivative was defined as that limit. So that's what we're kind of saying here, just a little bit more formally, except with an epsilon delta. And let's actually, and this is sort of a review of Calc 1, let's go back and actually we'll use this definition. Again, we'll be using both of these. This is kind of the more formal definition here for all epsilon greater than 0. This is true, but this is another definition. Like back in Calc 1, they called this the definition of the derivative. And let's go ahead and use this form to sort of review what you did in Calc 1. Especially helpful since a lot of you will be teaching Calc 1. So let's take a look at some examples here. Use the definition of the derivative. To find the derivative of, let's say, let's do several of these. Let me do this one first. Fx equals x cubed for x in the reals. And a lot of times you can just use a particular, we'll just use like a generic point C, and that'll give us the derivative of a particular point. There are other ways to do it, but I would just use like, say, a generic point C. So then F prime C XC FX. So remember, write down, we don't have to write this out every time, just to remind us of the definition. So what we want to do, we want to find the derivative at, say, a point C, we have to use this equation. And so let's just plug in what we have up here. Limit as x approaches C, so we'll put in x cubed minus c cubed over x minus c like this. And then we'll say, now we'll have to we need to get rid of this denominator somehow. Let's factor the numerator. And a lot of times I forget how to factor a trinomial. And so I sometimes have to play with it. But it factors like this. because I usually don't have to factor these very often, but that's the way it'll factor like that. And then then we factor, in other words, I just factored out an x minus c, and we end up with this. And of course, that cancels real nicely here. And you remember from Calc 1, again, if you have like just a polynomial, remember, if you're trying to find the limit of a polynomial, all you have to do is substitute your value in, because you're never in any danger of dividing by 0. So let's just put in our numbers. And that's just going to be c squared plus cc plus c squared is going to give us 3c squared back. And of course, so in other words, for any c you'd put in here, for any point, you end up with 3c squared. Of course, obviously, if you use the rule of the derivative, it's just going to be 3x squared. So that's the same thing we got here. Any questions on that? And so let's look at another one. Again, usually just a matter of playing with the equations. So f of x, and we just call it something different, just so we have a different name here. Call it g of x is 1 over x. Again, for x in R. So once again, we just want to find the derivative using the definition of the derivative. And also for x not equal to 0, because obviously it's not going to be defined for x equal 0. So just use the rule. And again, you don't have to write this down every time, but sometimes I find it be a good reminder what we're doing. We're going to put it into here. And approach is c, and then 1 over x. And then just plug in to your function 1 over c, x minus c, like this. And again, a lot of times you have to play with something like this. Usually a good start is always to find the common denominator. If you have two fractions like this, find the common denominator. Will usually, if it doesn't give you the answer, it'll kind of give you an idea where to go. And so if we take c x minus, cx over c, c over cx, and then x over cx divided by x minus c, this. And then we can say the limit as x approaches c, c minus x over cx, x minus c, like this. And we can then, now notice that these are going to be opposite signs, so we'll have to change one of them. We'll make this, I'll make the numerator over here, I'll factor out a -1 so that it looks like the denominator, x minus c. All I did was factor out a -1. Then I'll bring the other ones down into the denominator. And that's going to be, and then it's cx, x minus c, and then these cancel. x c, and then we're going to have 1 over cx. And once again, as long as we said at the beginning here, x can't be 0, remember, if you're doing a limit and it's approaching c like this, there's no chance of dividing by 0. You can, at this point, you can just substitute. And that's and I forgot my negative, sorry. When these cancel, there's a negative right here. And then this is going to be minus 1 over cc minus 1 over c squared, like that. Any questions like that on that? Questions at all? And let me just do a couple more. Again, you probably did this when they first introduced you to derivatives. You did a bunch of these, and then you learned all the derivative rules after that. And then you probably haven't had a lot of occasion to use it since then. So let's do this. I'm going to just do all these different ones just to get used to how to reduce these. And again, there's a lot of overlap what we did before, kind of the same techniques. So we're going to find this one now, derivative of this thing. And once again, x approaches c. Just remember what we're doing. F of x minus fc divided by x minus c. That's the rule that we have to work with. And then this is equal to, if we plug in our function, it's going to be square root of x, square root of c over x minus c. Once again, anytime you have something like this, maybe I shouldn't speak too quickly. What would be the best? Should we maybe multiply? Well, actually, there's a couple ways you could do this. This maybe isn't quite as obvious, but like, for example, you could factor out a square root of x minus the square root of c under here. And that's probably the quickest way. Let's see if we can do that. So let me just put a box in here just to, let's just test that just to be sure. So note that the square root of x minus the square root of c times the square root of x plus the square root of c is equal to, then we multiply these two together, we get x. Multiply this, we get square root of x, square root of c, positive, and multiply these two together, square root of x, square root of c, negative, and then we multiply these two, we get minus c. And of course, that's going to give us x minus c. So we could factor the denominator this way, huh? So this is just maybe scratch work again. So again, let's just go back down here. So we'll factor the denominator that way and just say the limit x approaches c, square root of x, square root of c, square root of x. So what do we say here? We can factor this into this. square root of x, square root of c like this. And then these will cancel. And we have the limit x approaches c 1 over square root of x plus square root of c. And once again, oh yeah, up here we specified x was greater than 0. So once again, when you get to this point, you can just plug in the limit, and that's going to give us 1 over 2 square root of c like that. Any questions on that? And of course, on all of these, you can see by going by the rules, that would be the derivative of this. You know, it would be just, because this is x to the half, you know, and then you take, that'd be a half times x to the minus a half, which is just that. So let's just see now, again, that's probably the quickest way, but if we didn't see that, let's see maybe an alternative. Like I said, a lot of times when you see this, I usually think of the multiplying by the conjugate to get rid of the square root. So let's try that. So let's try an alternate way, just so you have other ways to do these. Alternate way. So when we're at this point here, and especially in a lot of your classes, you'll use the conjugate a lot. In fact, you probably have already. I know some of you are taking complex analysis now. You use it a lot for complex numbers. So it's good to always keep that in mind too. And x. So once again, remember the conjugate is you just take, let's say whatever we have here. If this was a positive, we would multiply it by square root of x minus square root of c over square root of x minus square root of c. If this is a negative, we multiply by the positive version. So just multiply this by square root of x, square root of c, square root of x, square root of c. Once again, we're allowed to do that because it's just multiplying by 1. And then the numerator, once again, if you multiply it out similar to what we did up here, you would find that's going to be x minus c over x minus c square root of x square root of c like this, and these will cancel. Limit x approaches c square root of x square root of c, and put the values in, and this would be 1 over 2 squares. Yeah, I guess this was just as fast as the other way. Any questions on that? And let me do just one more, just to put those two things together. Let's do this one here. This D. I call this K. 1 over square root of x for x greater than 0 again, and find the derivative. And so K prime would be the limit as x approaches, and actually should probably have a c in here to be technically correct. I'm finding the derivative of a particular point c, and that's going to be c, give me fx, that's fc, x minus c, plug everything in, And that's going to be 1 over the square root of x. That's 1 square root of c. And x minus c. Oops. And then, so we have that. Then, again, there's probably a lot of ways to do this. Maybe we can find a common denominator. And yeah, let's try that common denominator. Or we could factor, yeah, let me do, this is probably going to be the most obvious way. So if we do a common denominator in the top, we'll do square root of x or square root of c like this minus square root of x, square root of c, square root of x over x minus c. And multiply this out. Square root of c minus square root of x, square root of c, square root of x. And let me kind of bring that down in the denominator. And so that's going to be x minus c like this. And let me see, would be the quickest way, maybe like before. Yeah, let me just do the conjugate way again. And limit x approaches c, square root of c, square root of x, square root of c, square root of x minus c, and multiply by the conjugate, square root of c. And remember, whatever this one is, you change the sign over square root of c, square root of x, like this. And when you multiply the top out, you end up with c minus x, square root of c, square root of x, x minus c. Once again, you could skip a lot of these steps if you like. I just want to show everything. And we could factor out a negative up here. And so we'll make this a negative x minus c, square root of c, square root of x, x minus c, square root of c, square root of x. Cancel these out. And that's going to give us a -1. Square root of c, square root of x, square root of c, square root of x. And now if we put our c in, that'll give us let's see, just be sure. Yeah, we'll put our c in here minus, and this is, let me just put all the steps in, square root of c like this, square root of c, square root of c like this. And then this is going to be -1 over, that's going to be c. And this is going to be 2 square root of c. Let me write it as I said it so it's real clear. -1 And then we can call that a 2c to the 3/2, huh? Yeah. Any question on that? See if that all makes sense. Now we can always, again, we could just double check it. Now, usually we're doing we usually need to know this because in cases where we can't do the derivative with a rule, but let's just double check it. So if we check this, so if we're given k of x equal 1 over the square root of x, that's going to be equal to x to the what, negative 1/2. And then if we use the rule, bring the negative 1/2 down, x to the minus 3/2. And if we want to rewrite that, we could rewrite that as negative 1 over 2x to 3/2. So it looks like we got the same thing. Any questions on that? Any questions at all? Take a look at a couple more things here. So yeah, so those are some, I guess that's a review of Calc 1. And so let's keep in mind a couple things about, say, the hierarchy of, like, say, functions. Again, this is helpful, again, if you're especially if you're teaching Calc 1. And so at a point C, you may have, say, the limit of a function exists at C. The function may be continuous at C. And the derivative of a function may exist at C. So, and we can't have any of these without the previous. For example, a function cannot be continuous at C without the limit existing. And you can't have the derivative at a point C without it being continuous at C. So you have to have, again, before you can have function to have its derivative, it has to be continuous. For it to be continuous, the limit has to exist. And of course, going the other way, if you have one of the lower ones, then you automatically have the ones above. So if you know that the derivative exists at C, then you automatically know it's continuous. You automatically know the limit exists at C. Any questions on any of that? Let me go through some more rules that you had from calculus. Those. Let's take a look at and let's jump to this one. Let's go to the chain rule. And this is almost the way you had it in calculus. Let I and J be intervals in the reals. And let G be a function from I to the reals. And F is a function from the interval J to the reals. And again, so if you have this function, it's going to the F on the interval J, it's going to be a subset of I for this to work. And let C, B, and J if F is differentiable at C. And if G is differentiable at F of C, then the composite function G circle F is differentiable at C. And F circle C prime at C is equal to F of C dot F prime C. And you remember this notation, notation, remember G circle F is equal to, say it F as X. This is just the same thing as saying G FX, like this. So that's all that means. So again, when you take the derivative of this composite function, you end up getting this here. You take the derivative of the function itself, and you have the function FC in there, then times the derivative of this inside. We'll do some problems a little bit later on this. And then just note some of the notation here is that F of J has to be a subset of I. So let's just sort of maybe make a picture of that. So if you have, for it to work, you need something like this. So G, I'm not sure, let's see, maybe, let's put G, let me put J up here. So we have some kind of a interval J here. And this are interval column J. And then we have another interval down here. It could be wider or narrower. Have another interval I down here, let's say. And so, and call this I. So the function F, according to the rule here, it's got to be it's got to map into a subset of I. And then G will be a function on I like this. That's just sort of a technical thing to say that for this to work, since G is defined on I, F of J has to be a subset of I. So you can say something like this. It's got to be a subset of I like this, because G is just defined on I. So that if this was not a subset, if it could go into something bigger, then it wouldn't necessarily be defined, because G is only defined on the interval I. And that's just to give me an idea why they have to have these technical things here. And let's do a couple more here. This is 1.8 theorem. Let I be an interval. And let F be a function from I to R be strictly monotone on I. And again, remember, strictly monotone just means strictly greater or strictly lesser for each value. And let J be defined as a function on I. And let G be a function from J to the reals, be strictly monotone. And also, and G is the continuous inverse to F if F is differentiable at C in I, and F prime of C is not equal to 0, then G is differentiable at F of C basically, which is just, call this D of C, and G prime of D is equal to 1 over F prime of C, which is equal to 1 over F prime of G of D. And so I just want to write that down for the moment. And we'll do some examples to make a lot of this a little bit clearer next time, but we don't really have enough time to do it right now. Any questions on any of this? Yes, sir.
What's differentiable mean?
That you can take the derivative at a point. Yeah, it kind of just means that, yeah, that's a good question. So let's write that down. So differentiable means you can take the derivative, at the point at let's say C, and the derivative exists. So in other words, and the derivative so for example, once again, our friend 1 over X is always a good example. If we were to take the derivative of it we would get what? Minus 1 over x squared is not defined at x equals 0. So we would say in this case, so we say fx 1 over x is not differentiable at x equals 0. Yeah, good question. Any other questions?